All right, you guys, hi, welcome to homework question or homework help for rotation number 3. Now, I started to record this video about a minute ago and I got a phone call interrupting me here on my phone, which stopped the movie. So I apologize, I already have the writing. I had already done number 1. Look at that, it's over, you missed it. No, I'm kidding, I'll go back over it. Number 1 is a very straightforward moment of inertia question. What I was suggesting is to go to page 278 in your book, look up your geometric shapes, and find the proper shape for that particular, that particular description, which is a thin, solid door, obviously rectangular, and, plug and chug. Pretty straightforward stuff. We get to a little more of a meaty question here. And, all right, so, and it may even, the way it's phrased may even, strike you a little bit. Perpendicular to the page, passing through the fisher's hand. Okay, so we want to know what the heck the fish is doing. And obviously the fish is over here, going this way. But the rod, the fishing rod, goes this way. And the main thing that we need to keep in mind is that torque is, you're going to get your best torque when the force is applied at a 90-degree angle to the bar, or in this case, the fishing rod. All right, you want things at a 90-degree angle. So I really kind of want the force here. But notice how they drew my angle for me. So I think what might make it a little bit easier to see and to incorporate some of the stuff they've done for me here, I'm going to extend this bar. I realize it's still only, 1.8 meters on my page. Whatever they tell you the length is, you're going to work with that value, of course, for your radius. But let's extend this and go this way. So this is really the force that we want, okay? It's equivalent to that one, but this makes better sense incorporating these angles right here. Now, according to the question that I have, they have 94 newtons, and that goes over here. It's the hypotenuse, this little guy right here. And since I know the angle, we're looking at a sine function. So you want to find this, find your force here, and then of course your radius is the length of the pole. And that should make it pretty straightforward. But the main thing here is you have to figure out which force is actually perpendicular to the rod, because the original tug from the fish is not entirely perpendicular to the rod. It's only the sine piece. Okay, next one. Find the net torque on the wheel given, blah, blah, blah. You've got two different axes of rotation, or two different radii, really is what I mean to say. And, all right, you're given centimeters here. You're going to want to change those to meters, I'm not going to lie. Don't be fooled by the 30 degrees. See, what you want, what you're looking at here, this 12 newtons that they're giving you in the diagram is perpendicular to that little radius of A. Okay, just like this one, this 10 on the top is perpendicular to the radius of B, and so is the 9 newtons is perpendicular also to radius B. So you don't have to do anything with that 30 degrees. That's just to kind of throw you off. What you do need to realize is that direction matters. So what you want to ask yourself is, which way, because this one points that way, which way will this thing turn? If I only think about the 10 Newton force at the top, it's going to spin this way, all right, which is clockwise. And this one is going to do the same thing. This one is going to go counterclockwise. So positive direction, according to our question, is counterclockwise. Just watch your negatives and your positives. That one's actually not too hard to figure out. Once you figure out that the 30 doesn't really do anything. Okay, number 4, negligible mass. Okay, it's very helpful that the rod has a negligible mass. Otherwise, we're going to have to help. We're going to have to do bunches of stuff with that too. So you have 3 particles in a system, and you notice they're rotating around this axis X, which they give you. So what's going to become rather important is, how far away from my point of rotation are each of these 3 particles. All right, moment of inertia about the x-axis. If you're dealing with a system of particles, remember you're going to take the sum of each mass times the radius squared, and you're going to do that for each of the 3 particles, and then you'd add them up. Total rotational kinetic energy evaluated from this. I do believe they tell you the good old angular speed. And remember, their linear speed may be different, but their angular speed is the same because they're rotating together. But the linear speed is based upon the radius, so that is going to be different for both. And oh my goodness, look at this, tangential speed. You're going to use your relationship of angular speed to times the radius to give you the linear, and then of course total kinetic energy evaluated from, notice they're using the linear value here, so we want to see all of those kinetic energies added together. Sorry, I'm trying not to get too far from the microphone. I forgot to bring my microphone today, so I want to make sure that you can hear what I'm talking about. Okay, so make sure you add all those kinetic energies together and you should be good. That one's not too tough either. This one's actually a little bit tricky until you realize you just need to use the Pythagorean theorem. Okay, it says it rotates in the xy plane about the z-axis. Okay, now I know I'm a terrible artist anyway, but even if I weren't, I can't really draw this very well. Okay, so my z-axis is really kind of going like this. You know, it is in the third dimension. So the thing to keep in mind is that you know the value of the y-axis, and here's of course my center, my rotating, I'm rotating about that point. So what you need to do is find the radius in the z direction for each of these points. And I'll give you a hint, it's the same if you haven't figured that out, because you know, if you break these up into little rectangles, all the rectangles are identical in terms of the lengths of the sides. So the radius in the z direction is going to be the same as well. But you're going to need to use the Pythagorean theorem for that. So once you do that and you actually find the radius, again, we're going to come back down to that whole idea of, you know, a system of particles. And let's take them and add them all up. All right, so if we're going to do I need inertia? Yeah, that's the first one, part A, sorry. Lost my train of thought there. All right, but I want to take each of those 4 individual particles and I want to do the mass times the radius squared, and I want to add them together. Okay? And then when I want to do the rotational energy of the system, we're talking kinetic energy there, of course, because it's rotating, and yeah. So considering you will have the moment of inertia, this should not be too tough to do because they're already telling you the angular speed. All right, so hopefully that is helpful for you guys, and on to rotation 4 in a few minutes.